On Chicago's unpaved streets in the 1850s, whole houses did not stay where they were built. They were business assets on skids. Contemporary accounts describe buildings cut loose from their utilities, jacked up from their foundations, placed on greased skids resembling railroad tracks, and then pushed down the street by horizontal jacks at a slow, steady pace. At the same time, on the high plains and in the central Rockies, log houses were going up on shallow stone piers or wood sleepers beside snow-fed creeks, cheap, fast, close to water, and vulnerable to bank erosion during spring melt. This episode follows one representative mountain cabin through a full melt season in the 1880s using documented house-moving practice, log-building manuals, and modern hydrology to reconstruct how a greased pole, rope track, could move a finished log house, upslope, a foot at a time, without racking the corners, cracking the chinking, or breaking a single sill. The question is simple. When the bank starts moving first, can the cabin move fast enough, without breaking itself? Frost still lingered in the roof shade at dawn. By mid-morning, the creek was running high and brown, carrying branches and chunks of ice past a small log cabin perched on a low alluvial bench. The water moved fast enough to make a constant hiss against the banks. Every few hours, a larger piece of driftwood would slam into the cut bank behind the cabin, sending a shudder through the gravel. The bench had been chosen for exactly the reasons most mountain homesteads were sited: level ground, easy access to water, and a short haul from timber. The creek provided drinking water, a source for livestock, and a natural corridor for moving logs during construction. The bench itself was broad and flat, built up over decades from layers of stream-deposited gravel and silt. In a dry year or a mild winter, it looked stable, permanent, safe. But snowmelt-driven streams in high mountain valleys do not behave predictably year to year. Modern hydrologic analyses show that such creeks experience sharp late-spring flow peaks driven by rapid snowpack release. When warm rain falls on existing snow, or when a sustained warm spell hits in May or June, weeks of accumulated winter precipitation can release in days. Water volume surges. Flow velocity increases. Shear stress at the channel bed and banks multiplies. The banks respond. Unconsolidated alluvium, the same gravel and silt that made the bench easy to dig and build on, erodes rapidly under sustained high water. A cut bank that appeared solid in October can retreat several feet during a single melt event. The process is not gradual. Banks fail in slumps and undercuts, entire sections collapsing at once when the supporting material beneath is scoured away. The cabin measured roughly 14 feet by 18 feet. Wall height stood at 8 to 9 feet, built from logs 6 to 8 inches in diameter at mid-span. The logs were local. Conifer, mostly lodgepole pine and Engelmann spruce, selected for straightness and uniformity. Corners were saddle-notched, a technique that interlocked the logs at 90-degree intersections without needing metal fasteners. The gaps between logs were chinked with wood blocks or small stones, then daubed with a mixture of clay, sand, lime, and straw to seal against drafts. The foundation consisted of dry-laid stone piers, stacks of flat rocks placed at the four corners and at intervals along the sills. The piers raised the bottom logs 12 to 18 inches above the ground, providing clearance for drainage and air circulation. This was standard practice. It kept the lowest logs from sitting in damp soil, which would accelerate rot, and it allowed rodents and small animals to pass underneath, rather than nesting against the wood. The rear wall of the cabin stood perhaps 15 feet from the creek at high water. When the homesteader had staked out the site 2 years earlier, that distance had been closer to 25 feet. The creek had moved. Fluvial geomorphology studies from similar Rocky Mountain valleys document lateral channel migration rates on unprotected alluvial banks. During peak flows, erosion of 1 to 3 feet per event is common. Over multiple high water seasons, total retreat can exceed 10 feet. The process accelerates once a cut bank begins to undercut. Water scours beneath the bank toe, removing support, and the overlying material collapses into the flow in large blocks. The homesteader had noticed the change. Last spring, a willow thicket had stood between the cabin and the water. This spring, the willows were gone, and raw gravel showed where the bank had slumped away. The rear stone pier on the creek side now sat closer to the edge than was comfortable. If the bank continued retreating at the current rate, the pier would be undermined within one more melt season. When that happened, the rear sill would cantilever over empty space. The log shell would begin to settle unevenly, twisting and racking the carefully fitted joinery. Everything above the foundation was sound. The logs had seasoned properly. The chinking was tight. The interior included a plank floor on hewn joists, a small stone hearth with a clay and stick chimney, and walls that had been hewn smooth on the interior faces. The cabin represented several months of skilled labor, along with materials that could not be replaced quickly. Cut nails for the floor, a few panes of real glass for the window, and the accumulated daubing that sealed every gap against the high-altitude cold. Losing the cabin to bank erosion would mean losing all of that. But moving it seemed nearly impossible. The homesteader stood outside the rear wall, measuring the distance from the sill to the crumbling edge. 15 feet now, maybe less. One good storm, one sustained warm spell that dumped rain onto the remaining snowpack higher in the valley, and the cut bank could retreat another. 3 feet in a single day. The same alluvial gravel that made digging piers easy now gave way with every high-water surge. What had been an advantage during construction was now an existential threat. A cold draft snaked through a chink line near the floor while midday sun warmed the south wall. Inside, the quality of the construction became clear. This was not a rough shelter thrown together in haste. It was a carefully engineered dwelling built to standards that balanced available materials with long-term durability. The wall system followed techniques developed over centuries in northern and eastern Europe, then adapted through Appalachia and carried west with the frontier. Each log course was leveled before the next was laid. The saddle notches, semicircular cuts on the underside of each log where it crossed a perpendicular wall, were shaped to fit tightly against the log below. This interlocking created structural rigidity without needing corner posts or metal fasteners. The inner faces of the logs had been hewn flat with a broad axe, creating smooth interior walls that reduced the volume of air to heat and eliminated bark-shielded spaces where insects could nest. The outer faces remained round, which was faster to build and provided more mass for thermal stability. Between the logs, the gaps were first filled with wood blocks or flat stones, the chinking then sealed with daubing. The daubing mixture was critical. A proper recipe combined clay for plasticity, sand for structure, lime for setting strength, and organic fibers, straw, animal hair, or grass, for reinforcement. The fibers prevented shrinkage cracks. The lime created a mild hydraulic set that made the daubing more resistant to water damage. The result was a flexible, vapor-permeable seal that accommodated minor seasonal movement in the logs without cracking open. This cabin's daubing included cow hair obtained from a ranch down valley. The hair had been chopped into short lengths, mixed into wet clay along with sand and a small amount of slaked lime, then troweled into the chink lines from the interior. After drying, it formed a hard but slightly flexible seal. When tapped with a knuckle, it rang solid. The floor was another mark of care. Many frontier cabins had packed dirt floors, or at best a single layer of split logs laid directly on the ground. This cabin had a proper floor system, joists hewn flat on top, spaced roughly 16 inches on center, spanning from sill to sill. Over the joists lay planks sawn at a small water-powered mill 20 miles down valley. The planks were nailed with cut nails, expensive but far superior to wooden pegs in holding power and durability. The hearth occupied the center of the rear wall. It was built from flat stones gathered from the creek bed and mortared with clay. The firebox was small but efficient, designed to burn wood in short, hot fires rather than smoldering all day. Above the firebox, a clay and stick chimney rose, through the roof lined with smooth stones to protect the clay from direct flame. The hearth and chimney base added several thousand pounds of thermal mass, stone that absorbed heat during fires and radiated it back into the room for hours afterward. The window was a single pane of real glass, 10 inches by 12 inches, set into a frame notched into one of the logs on the south wall. Glass was fragile and expensive on the frontier, but it allowed light and passive solar heating in winter. A wooden shutter hinged on the interior could close over the glass for security or insulation. Preservation briefs written a century later emphasized that historic log buildings should, whenever possible, be moved or stabilized in ways that preserve original foundations, sills, chinking, and finishes. These elements are not just structural, they are integral to the building's thermal performance and historical significance. Dismantling a log cabin and rebuilding it elsewhere means losing the tight fit of seasoned joinery, the tuned thermal mass of the daubing, and the proven interior climate that results from years of settling and adjustment. Frontier myth often treats log cabins as rough, disposable shelters, adequate for a season or two, then abandoned. In reality, many were carefully engineered and represented substantial investment. Felling, hauling, peeling, and shaping logs took weeks. Notching corners and leveling courses required skill. Chinking and daubing were slow, repetitive work. A well-built cabin could last decades with minor maintenance. Tearing it down to escape a failing site meant throwing away months of labor and starting over from raw timber. The homesteader understood this. He had built the cabin himself over the course of one summer, using techniques learned from his father in Pennsylvania. The logs were sound, the chinking was tight, the floor was level. The hearth drew well and kept the interior warm even when outside temperatures dropped below zero. The cabin was heavy, but its real weight was in the work already invested. Hairline cracks appeared in the daubing along the rear wall, visible in raking morning light. A tin cup of water on the table sat slightly out of level, the surface tilted enough to catch the eye. Outside, the creek ran fast and opaque with suspended sediment, the color of milky coffee. The sound was constant, a low roar punctuated by the thud of driftwood against the banks. The bank was failing, not dramatically, not all at once, but in increments that added up. Each high-water pulse scoured a little more material from the toe of the cut bank. Small blocks of gravel and root-bound soil slumped into the current. The process was visible hour by hour, fresh scars on the bank face, new roots exposed and trailing in the water, clods of overburden collapsing into the flow. The rear stone pier on the creek side now stood within 2 feet of the new bank edge. The pier itself had not moved, but the ground supporting it had. Beneath the stacked stones, the alluvium was eroding from the side, creating a void. The pier leaned slightly toward the creek, no more than an inch or two out of plumb, but enough to transfer uneven load to the rear sill. Inside the cabin, the effects were measurable. The rear sill had settled relative to the front, dropping perhaps half an inch. That small difference was enough to put stress on the entire log shell. The saddle-notched corners, which relied on even bearing at all 4 points, were now carrying unequal loads. The rear corners compressed slightly. The front corners, bearing more weight, compressed more. The differential movement opened gaps between log courses, not large gaps, but enough to let light and air through. Doors and window frames, which had operated smoothly, now bound in their openings. The front door, hung on leather hinges, scraped the floor when opened. The window shutter, previously a snug fit, now had a visible gap at the bottom corner. These were early signs of structural distortion. If the settlement continued, the gaps would widen, chinking would crack and fall out, and the log shell would begin to rack, twisting in plan, with opposite corners lifting or dropping. The homesteader checked the plumb of the rear pier with a weighted string, 2 inches out of vertical. Not catastrophic yet, but trending wrong. He walked the bank line, inspecting the scour patterns. The cut bank was now vertical for the upper 3 feet, undercut for perhaps another foot below that. The undercutting meant the bank was unstable. When enough material eroded from beneath, the upper section would collapse all at once, potentially retreating another 2 or 3 feet in a single event. Modern river restoration reports from similar Colorado mountain valleys document how bank erosion progresses once structures or other fixed objects encroach into active channels. In flood years, sudden lateral retreat of 5 to 10 feet is not uncommon on unprotected alluvium. The process is nonlinear. Erosion accelerates as the channel finds weak points, then slows when it reaches more resistant material or a wider cross-section that distributes flow energy more evenly. In this case, the cabin had been built on the assumption that the creek was stable. 2 mild winters had reinforced that assumption. The channel had not moved noticeably during those years. But the assumption was wrong. Snowmelt-dominated streams in steep mountain valleys are inherently dynamic. They adjust their position in response to flood magnitude, sediment supply, and the resistance of bank materials. A cabin sited 15 feet from the channel might be safe for 5 years, then suddenly vulnerable in the 6th. The decision tree was clear. Do nothing, and the rear pier would fail within weeks, possibly days if another high-water pulse came through. Once the pier failed, the rear sill would cantilever over empty space, and the entire log shell would begin to collapse. Dismantling the cabin and rebuilding it farther back would take the rest of the summer and risk damaging the carefully fitted joinery, the tight chinking, and the seasoned logs. Attempting to drag the building as a unit using chains and a team of animals would likely rack the structure beyond repair. Sudden jerks and lateral forces would crack the corner notches and shear the daubing. The third option was to treat the cabin as a controlled load, jack it off its piers, support it on temporary cribbing, then move it as a single rigid unit using a low-friction track and slow, steady pulling. This option required understanding principles that urban house movers had already worked out and adapting them to mountain conditions with the materials at hand. Everything above the sills was sound. Everything below them was moving. The next move had to be the cabins. A balloon frame house inched along a Chicago street, moving so slowly that pedestrians could step aside without hurry. The building sat on heavy timbers that extended beyond the walls on all sides, forming a platform. Beneath the timbers, greased wooden rails, skids, ran parallel to the direction of travel. Horizontal screw jacks pushed against posts set in the street behind the house, advancing the structure a fraction of an inch with each turn of the jack handles. The scene was routine enough in mid-19th century Chicago to have become a civic nuisance. City council records from the 1850s include petitions from merchants and residents complaining about house-moving operations blocking streets for days at a time. Buildings were business assets. When a lot owner wanted to reclaim the land, or when a building needed to be relocated to higher ground or onto a different street grid, the structure was simply moved. No one tore down a usable building if it could be relocated instead. The technique was straightforward. Workers jacked the building off its foundation, inserted timbers underneath to form a platform, then placed the entire assembly onto greased skids. The skids were described in contemporary accounts as resembling railroad tracks, 2 parallel wooden beams greased on top to reduce friction. Horizontal jacks pushed the building along the skids, advancing it a few inches per cycle. When the building moved forward, workers picked up the skids left behind and carried them to the front, creating a continuous path. The process could move a two-story frame house several blocks in a week or two, with work proceeding slowly enough that occupants sometimes remained inside during the move. The key principles were clear, even if the participants did not describe them in engineering terms. First, reduce friction. Wood sliding on greased wood required far less force than wood dragging across dirt or gravel. Second, spread the load. A building concentrated onto 4 corner posts would punch through soft ground. A building supported on a platform bearing on long skids distributed weight over a much larger area. Third, move slowly. Sudden jerks or starts created dynamic loads that could crack plaster, shift walls, or even collapse poorly braced structures. Slow, steady motion kept loads within the elastic range of the materials. Fourth, maintain control. The continuous skid path and the use of mechanical jacks meant that movement could be stopped instantly if something shifted or misaligned. Contrast this with dragging a building on chains with a team of animals. Once the team started pulling, stopping was difficult, and if the load caught on an obstacle, the sudden jolt could cause severe damage. The Chicago house-moving practice was enabled by balloon frame construction. Balloon frames used light dimensional lumber, 2x4s and 2x6s, nailed together to form walls and floors. The result was a strong, lightweight structure that could flex slightly without failing. Log cabins, by contrast, were heavy and relatively inflexible. A log building's mass came from the logs themselves, solid wood 6 to 10 inches in diameter, stacked to form walls 8 or 9 feet high. Total weight of even a modest log cabin could approach 10 tons. But the principles still applied. If city crews could walk a block of balloon frame buildings down a street without breaking windows or cracking plaster, then a single log cabin could be moved using the same fundamentals: controlled jacking, temporary support, low-friction sliding surfaces, and slow, steady pulling. The difference was in scale and materials. Chicago had manufactured materials, sawn timbers, iron jacks, cut lumber. The mountain frontier had trees, stone, rope, and animal fat. But the physics did not change. Reduce friction, spread load, move slowly, maintain control. Apply those principles with the materials available, and a heavy object could be moved without destroying it. The Chicago house movers worked on flat, paved or graded streets. The mountain homesteader faced sloped, uneven ground covered in stumps and stones. Chicago movers had access to hardware stores and iron foundries. The homesteader had an axe, a saw, a shovel, and a broadaxe. Chicago movers could hire crews. The homesteader worked alone or with at most 1 or 2 neighbors. The adaptation challenge was real. But the core method was transportable. Greased skids became greased poles. Screw jacks became lever jacks or simple wedge and crib systems. Iron fittings became wooden lashings and pegs. Manufactured rope became rope spliced by hand from hemp or manila cordage. If whole blocks of city buildings could crawl without cracking, a single log cabin could too, if the physics were applied. A logging crew in the Pacific Northwest dragged a massive felled spruce trunk along a prepared path through the forest. The path was not a road in the conventional sense. It was a series of buried logs laid perpendicular to the direction of travel, half sunk into the ground, spaced every 6 to 8 feet. The top surface of each log was smooth and greased. The felled trunk slid over these skids with far less effort than it would have taken to drag it directly over dirt and stumps. This was a skid road, a logging technology that emerged in the Pacific Northwest in the mid-19th century and spread wherever large timber was being extracted. The buried logs formed a track. The grease, rendered animal fat or sometimes vegetable oils, turned the wood-on-wood interface into a low-friction slide. A team of oxen could pull loads that would have been impossible over bare ground. The principle was identical to Chicago's greased skids for house moving, but applied to a different problem. Loggers needed to move long, heavy logs from felling sites to mill ponds or rail sidings. Dragging logs over rough terrain tore up the logs, wore out chains, and exhausted draft animals. The skid road concentrated the hauling path, spread the load over multiple contact points, and reduced friction to manageable levels. Skid roads were often temporary. A logging crew would lay down a skid road to reach a stand of timber, use it for a season or two until the accessible trees were cut, then abandon the road and build another one elsewhere. The logs used as skids were typically smaller trees or offcuts that were not suitable for milling. Grease came from whatever was available, tallow rendered from livestock or fish oil in coastal areas. The functional parallel to moving a building was direct. A log cabin was, in essence, a heavy load that needed to move over rough ground. The same principles that made skid roads work for dragging felled timber could make a track work for sliding a cabin. Lay parallel poles to form a track. Grease the top surfaces to lower friction. Support the cabin on broad shoes or planks that bore on the greased poles. Pull slowly and steadily, keeping the load under control. The homesteader at the eroding creek site did not have to invent the concept. Skid roads were known technology on the frontier, used by anyone involved in logging or moving heavy timber. The adaptation required was simply applying the same concept at a different scale. Instead of moving a single log, move an entire log structure. The engineering question came down to load and friction. The cabin weighed perhaps 8 to 10 tons fully assembled. Dragging that weight over bare soil would require overcoming both the static friction of wood on dirt and the mechanical resistance of dirt piling up in front of the cabin's leading edge. Estimated force required, potentially several tons of pull, well beyond what a single animal team could provide, and almost certain to generate shock loads as the cabin alternately stuck and released. Placing the same cabin on greased poles changed the calculation. Wood on greased wood reduced the friction coefficient by roughly an order of magnitude. Instead of needing thousands of pounds of steady pull, the cabin might move with hundreds of pounds. The difference between impossible and merely difficult. The poles themselves needed to be straight, smooth, and strong enough to bear several tons of concentrated load without breaking. Diameter of 5 to 6 inches was adequate for spans of 10 to 15 feet between supports. Local conifers, lodgepole pine, spruce, or fir, provided suitable material. The poles would be felled, limbed, peeled to remove bark, and smoothed to remove knots or irregularities. Then they would be laid parallel in the direction of travel, spaced to match the width of the cabin's sills. Grease recipe was critical. Animal tallow rendered from beef or mutton fat was the standard frontier lubricant. It was readily available on any homestead that raised livestock for food. Tallow could be heated to liquid, brushed onto the pole surfaces, then allowed to cool into a slick, waxy coating. In warm weather, it remained pliable. In cold weather, it hardened, but still reduced friction compared to bare wood. Once you see logs sliding over greased logs, it's not a leap to imagine a house sliding the same way. A steel measuring tape ran from the rear sill to the crumbling edge of the cut bank, 4 feet, 6 inches. Then the tape extended upslope, following the proposed path to a new pier line marked with stakes, 62 feet. Vertical rise, approximately 3 feet, measured by sighting along a leveled board propped on stakes. The homesteader stood with a pencil and a scrap of paper working through the arithmetic. The load had to be defined before any movement could be planned. Guessing was not sufficient. Too light an estimate, and the track or rigging might fail under load. Too heavy an estimate, and excessive effort would be wasted on overbuilt systems. Wall logs first. 4 walls, 2 at 14 feet, 2 at 18 feet. Total linear feet of wall, 64 feet, running 8 feet high, with logs averaging 7 inches in diameter. Volume calculation gave roughly 40 cubic feet of solid wood per wall, or 160 cubic feet total for all 4 walls. Green conifer wood weighed roughly 40 to 50 pounds per cubic foot. Seasoned wood dropped to 35 to 40 pounds per cubic foot. The logs had been in place 2 years. Call them partially seasoned. Estimate 140 pounds per cubic foot, giving a total log weight of 6,700 pounds, just over 3 tons. Roof framing, ridgepole, rafters, purlins, and decking added perhaps another half-ton. Floor, joists, and plank decking, another half-ton. Total timber weight, 4 to 4.5 tons. Then the hearth. Stone hearth and chimney base, flat creek stones mortared with clay, forming a firebox and a short chimney extending through the roof. Volume of stone, approximately 3 cubic feet. Stone density, roughly 150 pounds per cubic foot. Weight, 450 pounds. Add clay backing and soil fill around the firebox, bringing the hearth mass to perhaps 1,200 pounds, another half-ton. Interior contents, minimal furnishings, tools, a few crates of supplies. Perhaps another 200 pounds. Total estimated weight, 5 to 5.5 tons. Call it 11,000 pounds to be conservative. 11,000 pounds was the weight of roughly 5 or 6 adult cattle. It was a substantial load, but not impossible. The challenge was not lifting it. Jacks and cribbing could handle that weight if the lift was done in small increments. The challenge was moving it horizontally over uneven ground, without racking the structure or exceeding the capacity of the rigging. The path itself had to be planned. 62 feet horizontal, 3 feet vertical. Slope, roughly 5% grade. Not steep by mountain standards, but enough to require careful control. If the cabin started sliding downslope on the greased track, stopping it would be difficult. The corridor was cleared by hand over the next several days. Saplings cut, stumps removed or cut flush with the ground, large stones pried out and rolled aside. The cleared strip was roughly 12 feet wide, enough for the cabin, plus a few feet of side clearance for workers and tools. Where the natural grade was uneven, shallow cuts and fills were made with shovel and mattock, creating a relatively level path. Drainage was considered. Small cross ditches were dug every 15 feet to intercept surface runoff and prevent the track from turning into a mud channel during rain. The new pier line was located on higher ground, 20 feet back from the active bank and 3 feet higher in elevation. Test probes with a steel digging bar confirmed firm bearing. The soil was still alluvial gravel, but here it was older and better consolidated, with some clay content that provided cohesion. The site sloped gently away from the creek, ensuring that any rain or snowmelt would drain away from the foundation rather than pooling beneath the sills. Stakes marked the 4 corners and the intermediate pier locations. String lines ran between stakes, defining the cabin's footprint on the new site. Plumb lines hung from the string intersections verified that the corners were square and level relative to each other. Knowing the load and distance allowed estimating required pole strength, rope capacity, and jack forces rather than guessing. The cabin's weight was now a number, not just a feeling underfoot. Freshly felled poles lay parallel on the cleared ground, their surfaces slick with rendered tallow. Each pole was a small conifer trunk, roughly 5 to 6 inches in diameter and 16 feet long. The bark had been stripped using a draw knife, leaving smooth, pale wood. Knots were shaved flush. The poles were not perfectly straight. Few trees are, but they were straight enough that when laid side by side, they formed a reasonably even surface. The poles had been selected and prepared over the previous week. Felling was done with a crosscut saw. Limbing was done with an ijamare axe. Bark removal required patience. The draw knife blade was drawn along the length of the log, peeling off strips of bark and the soft cambium layer beneath. The goal was a smooth surface that would not catch or bind against the cabin's shoes. Any irregularity, a protruding knot, a patch of rough bark, would create a high friction point that could stall the move. 14 poles in total. At any given time, 8 to 10 poles would be under the cabin, arranged in 2 parallel tracks running fore and aft under the main sills. The remaining poles would serve as spares, moved from back to front as the cabin advanced, a leapfrogging system that created a continuous track without needing dozens of poles. The poles were laid on the cleared path parallel to the direction of intended movement. Spacing between the two tracks matched the width between the cabin's two main sills, approximately 11 feet. Each pole was positioned to lie flat and stable on the ground. Where the ground was soft or uneven, flat stones were wedged underneath to provide bearing. Short stakes were driven into the ground alongside each pole to prevent rolling or lateral shifting. Cross ties, shorter pieces of timber, were lashed perpendicular to the track poles at intervals, forming a ladder-like structure. The cross ties held the track gauge constant and distributed lateral forces. If the cabin started to shift sideways during movement, the cross ties would resist, keeping the track aligned. The grease came from tallow rendered at the homestead. Beef fat had been boiled in an iron pot until the liquid fat separated from connective tissue and water. The pure liquid tallow was skimmed off and poured into a bucket. While still warm and liquid, it was brushed onto the top surface of each track pole using a rag wrapped around a stick. The layer of tallow was thin, perhaps 1/8 of an inch, but it transformed the wood surface. Ungreased wood-on-wood contact has a friction coefficient of roughly 0.4 to 0.5. Nearly half the force pushing down must be matched by horizontal force to start sliding. Greased wood-on-wood drops the coefficient to perhaps 0.1 to 0.2. Only 1/10 or 1/5 of the vertical load is needed as horizontal pull. For an 11,000-pound cabin, the difference was between needing 5,000 pounds of force to start movement, impossible, and 1,000 to 2,000 pounds, difficult but achievable with a simple mechanical advantage system. The tallow also had the advantage of being sticky and persistent. Unlike water or oil, which would soak into the wood or evaporate, tallow clung to the surface and remained effective over multiple movement cycles. In warm weather, it stayed pliable. In cold weather, it hardened slightly, but still reduced friction. Preservation manuals written a century later stress the importance of distributing loads over many points when jacking or moving historic log buildings. The principle is the same as that applied here. Avoid concentrating weight on small areas, which can crush wood fibers or punch through weak ground. The track poles extended, bearing length dramatically compared to simply dragging the cabin across dirt. Each pole in contact with the cabin's shoes provided 10 to 15 feet of bearing length. With 8 poles under the cabin at any time, the total bearing length was 100 feet or more, spreading 11,000 pounds to roughly 100 pounds per linear foot of pole. 3 inches of fat on a peeled pole could save 3 seasons' work above it. A heavy hemp rope lay coiled beside a freshly dug trench upslope from the new pier line. The trench was 3 feet deep, 4 feet wide, and ran perpendicular to the intended direction of pull. Buried in the bottom of the trench was a large log, a squared timber roughly 8 inches on a side and 6 feet long. This was the deadman anchor. The deadman was positioned with one end protruding from the trench, forming an upright post about 18 inches high. The trench was backfilled with soil, tamped in layers to compact it firmly around the buried log. The principle of a deadman anchor is leverage. Pulling horizontally on the post tries to rotate the buried log, but rotation is resisted by the soil pressing down on top of the log. The deeper the log and the longer its buried length, the more soil weight resists rotation and the greater the holding power. A 6-foot log buried 3 feet deep in compacted soil can resist several tons of pull before failing. The rope was manila, roughly 1 1/4 inches in diameter. Manila hemp rope was the standard for heavy hauling work on the frontier, stronger and more rot-resistant than native plant fiber ropes, available from suppliers in towns or by mail order. The working load of 1 1/4 inch manila rope was approximately 1,000 to 1,500 pounds under steady tension. adequate for moving a cabin if mechanical advantage could be arranged to keep actual rope tension below that threshold. The rope had been spliced into a continuous loop. Total loop length was roughly 200 feet. Splicing was done by unlaying the strands at each end, interweaving them in a specific pattern, then working the joint smooth. A proper splice retained 90% or more of the rope's full strength. A poorly made splice was a weak point that could fail under load. The loop ran from the deadman anchor post down the cleared path to the cabin, around or through a crossbeam lashed beneath the cabin's front sill, then back up to the anchor post. The geometry formed a closed loop. As you pulled on one segment of rope near the anchor, the entire loop rotated. The cabin, captured by the loop at the far end, was dragged toward the anchor. The mechanical advantage came from the ratio of rope motion to cabin motion. Pulling 1 foot of rope through the system moved the cabin only a few inches depending on the exact geometry. This was a trade, speed for force. Pulling slowly on the rope allowed a small crew, or even one person, to generate enough force to overcome the cabin's friction on the greased poles. The crossbeam beneath the cabin was a heavy timber lashed horizontally under the 2 main sills. The rope loop passed around this beam, forming a simple pulley-like connection. The beam spread the pull force across both sills, preventing the rope from concentrating load on one side of the structure. Control was built into the system. Wooden wedges, chocks, were driven into the ground ahead of the cabin's shoes, acting as temporary brakes. After each pull, before releasing tension on the rope, the chocks were hammered tight against the shoes. This prevented the cabin from sliding backward if tension was released suddenly or if someone lost grip on the rope. Redundant lashings served as catch lines. These were additional ropes tied to the cabin and anchored to trees or stakes behind the cabin with enough slack to allow forward movement but not backward sliding. If the main rope failed, the catch lines would arrest the cabin before it could slide downslope. Documentary records from 19th and early 20th centuries describe similar rope-driven systems in bridge building, railroad construction, and logging. Continuous loop rigging was common when moving heavy objects over uneven ground without access to mechanical winches. The principle was always the same. Turn intermittent, human-scale pulls into smooth, low-acceleration motion of a heavy load. The cabin would never move more than an inch or two per pull, but each inch was predictable. Stacks of cribbing timbers stood like short square towers at each corner of the cabin. Each stack was built from short pieces of squared timber, 6 by 6 inch or 8 by 8 inch sections, roughly 2 feet long, crossed and stacked like a log cabin in miniature. The cribbing provided stable, adjustable support that could be raised incrementally as the cabin was jacked higher. Atop each crib sat a lever jack, a simple device consisting of a vertical post with a ratchet mechanism and a long handle. Pumping the handle raised the post in small increments, perhaps a quarter-inch per stroke. Lever jacks were common tools on the frontier, used for lifting wagons, positioning heavy beams, and any task that required controlled vertical movement of a heavy load. The jacking sequence had been planned carefully. Raise each corner no more than 1 inch per cycle. Follow a circuit around the building, northeast corner, southeast corner, southwest corner, northwest corner. After each lift, insert additional cribbing under the raised corner, then move to the next corner. The goal was to keep all 4 corners rising at the same rate, maintaining the log shell as close to level as possible throughout the process. Lifting one corner too far ahead of the others would twist the structure, potentially cracking the corner notches or opening gaps in the chinking. The first lift began at mid-morning. The jack handle was pumped slowly, each stroke clicking the ratchet forward a fraction of an inch. The cabin's weight bore down through the sill log, through the jack post, through the crib stack, and finally into the ground. As the jack extended, the sill lifted, and the stone pier beneath lost contact with the bottom log. When the gap was roughly 1 inch, a wooden shim was driven into the crib stack to lock the height, and the jack was carefully relaxed. The corner now rested on cribbing, not on the original pier. The circuit continued. Southeast corner, pump the jack, insert shim, move on. Southwest corner, pump, shim, move. Northwest corner, pump, shim, complete the circuit. Then back to northeast for the next inch. By the end of the first day, all 4 corners were 12 inches higher than the original pier line. The stone piers that had supported the cabin for 2 years now sat unused beneath the raised sills, visible gaps of open air between stone and wood. The cabin's weight was entirely on the cribbing. Interior monitoring was critical. A plumb bob hung from the ridge beam, its point marking a spot on the floor. After each circuit, the homesteader checked the plumb position. If it shifted more than a 1/4 inch, the jacking sequence was adjusted to bring the structure back to level. The cabin door was opened and closed repeatedly. If it started to bind, jacking was paused and the situation reassessed. The window shutter was checked. Chinking lines were inspected for new cracks. Shoes were installed once the cabin was high enough. These were broad planks, 2 inches thick, 12 inches wide, 16 feet long, bolted under each main sill. The planks extended slightly beyond the front and rear of the cabin, forming runners that would bear on the greased track poles. The bolts passed through the sills and were clinched on the underside of the shoes, locking the two together. Cross braces and strongbacks tied the sills into a single rigid frame. Strongbacks were additional timbers lashed diagonally across the underside of the cabin, connecting front sill to rear sill on each side. These prevented the sills from spreading or twisting independently during movement. Inside, temporary diagonal braces were installed from floor to walls, running from the floor joists up to the log walls at a 45-degree angle. These interior braces stiffened the log shell, reducing the risk that horizontal movement would cause racking. Light furnishings were left in place as a test. A cup of water remained on the table. A small stove sat in one corner. If the move was truly smooth, these items should remain undisturbed. If the move was rough, the water would slosh and the stove would shift. Clear feedback that adjustments were needed. Once the last pier was clear of weight, the cabin was, for the first time since it was built, completely in human hands. Chalk marks on a stake beside the track recorded progress. 2 feet on the first day, 3 feet on the second, 1.5 feet on the third. The work developed a rhythm, not fast, but steady and methodical. The movement cycle began with preparation. Fresh tallow was brushed onto the forward section of track poles where the cabin shoes would bear during the next pull. The rear poles, those the cabin had already passed over, were pulled out from behind, carried to the front, and laid in position to extend the track. This leapfrogging kept the number of poles required manageable. 14 poles could build a track of any length as long as the crew was willing to keep moving them forward. Chocks were removed from in front of the shoes. The rope loop was checked for proper alignment around the crossbeam and around the deadman anchor post. Then tension was applied. The homesteader and one neighbor pulled on the free segment of rope near the anchor post. The rope tightened. The cabin resisted at first, static friction between shoes and poles, then released and began to slide. The motion was almost imperceptible, 2 inches, then 3, then stop. Total time for one pull, perhaps 30 seconds. Chocks were immediately hammered back into place ahead of the shoes. Tension on the rope was released carefully. The cabin was inspected, plumb checked, door tested, chinking examined. If everything remained sound, the cycle repeated. Net gain per full workday, with all cycles completed, averaged 2 to 4 feet. The variation depended on ground conditions, weather, and the need for adjustments. On the 4th day, when light rain softened the ground beneath one track pole, progress slowed to 1.5 feet as additional stakes and cross bracing were added to stabilize the track. On the sixth day, with dry conditions and a well-greased track, progress reached 4 feet. The slow pace was intentional. Rushing risked damaging the structure. Each pull generated force, but the force was applied gradually over several seconds, giving the cabin time to overcome static friction and begin moving without a shock load. Once moving, the shoes slid smoothly on the greased poles, and momentum carried the cabin forward a few inches before friction brought it to rest again. Friction management was continuous. After 10 or 12 pulls, the tallow on a given pole section would be partially wiped away or compressed by the shoes. When motion started to feel jerky, sudden starts and stops instead of smooth sliding, the crew paused to re-grease. Tallow was reheated in a small pot over a fire and brushed onto the worn sections of pole. Additional poles were sometimes added under high-load areas. The hearth section of the cabin, with its 1,000 pounds of stone mass concentrated in one area, bore more heavily on the track than the lighter wall sections. Where the hearth would pass, an extra pole was laid parallel to the main tracks, forming AAC 3-pole-wide section that spread the load. Structural feedback came from simple indicators. The cabin door was opened every evening after work stopped. If it swung freely and closed with the same gap at the top as it had the day before, the shell was not distorting. If it began to bind or if the gap changed, the rigging was adjusted. The window shutter was checked. The plumb bob was consulted. Chinking lines were walked and inspected for new cracks. Inside, the cup of water on the table remained level and undisturbed. The small stove had not shifted. These were the proof. The cabin was moving, but the movement was so controlled that the interior experienced no dynamic loads. By the end of the first week, the cabin had moved approximately 20 feet. The old pier line was visible downslope, stone stacks now isolated on the increasingly precarious bank. The new pier line was 40 feet ahead, marked by stakes and string. Halfway there. Documentary accounts from Chicago describe similar pacing when moving large buildings. A 2-story brick hotel was moved 6 blocks over the course of 3 weeks, with work proceeding 6 days a week, occupants remaining inside the entire time, and only minor cracking of interior plaster reported. The principle was identical: slow motion, careful monitoring, and immediate correction of any problems. By the end of the week, the cabin had moved farther than the creek had in 2 years. Overnight rain had fallen in the high country. By mid-morning, the creek was rising, its color shifting from brown to gray as fresh sediment load churned through the channel. Fresh wrack, twigs, grass stems, and bark fragments appeared several inches higher on the shrubs along the bank, marking the overnight crest line. The runoff spike was typical of late summer in the Rockies. Afternoon thunderstorms dump intense rain on high-elevation snowfields and bare rock. The water reaches the streams within hours, creating short-lived but powerful flow pulses. Modern hydrologic studies from similar valleys show that such events can temporarily raise flows to 50 or 70% of spring snowmelt peaks, with duration measured in hours rather than days. The homesteader walked down to inspect the old cabin site. What he found confirmed the necessity of the move. A slice of the cut bank where the rear pier had stood, where the cabin would still be standing if not moved, had slumped away overnight. The failure was clean, a vertical face 3 feet high, extending perhaps 4 feet laterally. The old pier site was now suspended over empty air, the edge of the bank a foot or more inboard of where the sill would have rested. If the cabin had still been on that site, the rear sill would have been cantilevered over the void. The log shell would have twisted as the rear settled, cracking chinking, jamming doors, and potentially collapsing. The move had been justified. Back at the track, ground conditions had softened. The rain had soaked into the topsoil, reducing bearing capacity. One track pole showed signs of settling, its downhill end sinking into softened ground. Stakes and additional cross ties were driven to stabilize it. Movement for the day was limited to shorter pulls, 1 to 2 inches instead of 3 or 4, and inspection intervals were increased. The reduced pace was frustrating but necessary. Pushing too hard on soft ground risked a sudden failure, a pole rolling out from under the cabin, or the shoes punching through the greased surface into the underlying soil. Either event could introduce a lateral shock that might crack the log shell. By August 18th, the cabin reached the new pier line. The stakes marking the 4 corners and intermediate pier positions were directly beneath the raised sill shoes. Alignment was checked using plumb lines dropped from the sill corners to the ground. The cabin was within 2 inches of the intended position, close enough. The new piers had been built during the movement days. Flat stones gathered from the creek bed were dry stacked into columns, each column roughly 18 inches square and 20 to 24 inches high. The height was set to keep the bottom sill logs well above the splash zone and drifting snow. The tops of the piers were leveled, using small flat stones as shims. A carpenter's level, placed across a straightedge, spanning between piers, confirmed that all piers were within a 1/4 inch of the same elevation. Lowering the cabin onto the new piers reversed the jacking sequence. The cabin was now supported on cribbing at each corner, with the new piers standing empty beneath. Jacking began at one corner. The lever jack was positioned on top of the new pier, its post extending up to contact the sill. Tension was applied to the jack to take the load, then the cribbing was carefully removed one piece at a time. The jack was slowly lowered, transferring the cabin's weight from crib to pier. The process repeated at each corner. As weight transferred to the piers, the cabin settled slightly, a few fractions of an inch as the dry stacked stones compressed and found their bearing. This was expected. The settlement would stabilize over the first few weeks as the stones locked into final position. The shoes and crossbeam were removed. Interior braces were taken down. The rope loop was coiled and set aside. The track poles were pulled out and stacked for future use or firewood. The cribbing was disassembled and stored. The hearth and chimney base were inspected. A few minor cracks had appeared in the clay mortar where stones had shifted slightly during movement. These were repointed with fresh clay. The chinking lines were walked one final time. A few small gaps had opened where individual logs had settled fractionally out of alignment. Fresh daubing was mixed and applied. The first real test of the new site came before the tools were put away and the cabin stayed dry. A plumb bob hung just clear of the EI rear sill, its string taut and still. The point touched a mark scribed into the stone pier directly below. The homesteader moved to the front sill, dropped the plumb again. The string aligned with another mark. The cabin was level within a 1/4 inch at all 4 corners. Inside, the door swung freely in its frame, the gap at the top uniform and correct. The window shutter closed snugly without binding. The final position of the cabin was measured relative to the creek, 52 feet horizontal distance from the rear sill to the current water line, approximately 3 feet higher in elevation than the old site. The bank was no longer a threat. If the creek continued to erode at the observed rate, 2 to 3 feet per major runoff event, it would take more than a decade to approach the new foundation. By that time, the channel might have stabilized or shifted entirely, as often happens when mountain streams reach a more resistant substrate or a wider valley floor. Structural outcome: no broken sills, no cracked logs, only minor touch-up required on chinking. The log shell had survived the move intact. The hearth was sound. The chimney had shifted very slightly relative to the roof line, perhaps a 1/4 inch, but not enough to affect function or require major repointing. The floor remained flat and solid. Labor accounting: 6 full days to clear the path and prepare the track. 3 days to jack the cabin, install shoes, and rigging. 7 days of actual movement, working half to 3/4 days. 2 days to lower onto new piers and perform final adjustments. Total: 18 days of focused work, with one neighbor assisting for roughly half that time. Compare this to the alternative: dismantling and rebuilding. Dismantling a log cabin without damaging the logs is difficult. The saddle notches lock the logs together. Removing one log requires lifting or prying the entire course above it. Daubing must be chipped out to separate logs cleanly. Interior finishes, plank floors, hearthstones, window and door frames must be removed and set aside. Each log must be numbered or marked to preserve the order of assembly. Total time to dismantle carefully: 2 to 3 weeks. Then rebuilding. Prepare a new foundation. Restack logs. Renotch corners if the logs have shifted or warped. Relevel each course. Refit floor joists. Relay floor planks. Rebuild the hearth and chimney. Reapply chinking and daubing. Total time: 6 to 8 weeks for an experienced builder working alone. Double that for someone less skilled. The rope track move had preserved not just the logs and stones, but the accumulated craft, the tight chinking that had been worked and reworked over 2 seasons to seal every gap, the floor that had settled and stabilized, the hearth that had cured and hardened over dozens of fires, the interior surfaces that had been shaped to fit specific tools and habits. All of this was conserved. Modern preservation guidance, written more than a century later, explicitly recommends moving historic log buildings intact when original sites become untenable. The reasoning is identical: dismantling risks, losing original material, breaking fragile joinery, and disrupting the thermal and structural integration that develops over years of use. A cabin that has been lived in for 2 or 3 years is not the same as a cabin freshly built. It has adjusted. Logs have compressed and locked into place. Chinking has filled gaps that only become visible after the first winter. The structure has become a system. Economic framing. The cost of moving was primarily time, 18 days of labor. The cost of rebuilding would have been primarily materials and time, new chinking, new daubing, possibly some replacement logs if the old ones were damaged during dismantling, plus 6 to 8 weeks of labor. Moving was cheaper by a factor of 3 or 4. The homesteader recorded the results in a small notebook used for tracking expenses and workdays. Moved cabin 52 feet upslope in 18 days. Structure sound. Bank took another 4 feet during last storm. Old site would have failed. 3 weeks of careful movement saved the results of an entire building season. A modern log building conservation drawing shows jacks positioned at each corner of a historic cabin, with cribbing stacks rising in neat square towers. Temporary steel beams extend under the sills, and hydraulic jacks replace the lever jacks of the 1880s. But the geometry is identical. The principles are identical. The practice of moving log buildings intact did not disappear with the frontier. Throughout the 20th century, as historic preservation became formalized, moving remained a standard technique for relocating threatened structures. National Park Service preservation briefs written in the 1980s and 90s stress that raising, leveling, and moving log buildings should be done in ways that preserve original foundations, sills, chinking, and finishes. The reasoning is consistent. These elements are integral to the building's significance and performance. The methods evolved, but did not fundamentally change. Wood cribbing gave way to steel beams. Lever jacks gave way to hydraulic jacks. Greased poles gave way to steel rollers or rubber-tired dollies. But the sequence remained the same. Jack the structure, insert temporary support, create a low-friction path, move slowly under control, monitor for distortion, and set on to a new foundation. The continuities are striking. Urban house movers in 1850s. Chicago used greased skids resembling railroad tracks. Frontier homesteaders in the 1880s adapted the same principle with peeled poles and tallow. Modern preservation crews in the 21st century use steel beams and hydraulic dollies. All three converge on the same solution because the physics does not change. To move a heavy structure without damaging it, reduce friction at the moving interface, spread the load over multiple contact points, move slowly to avoid dynamic loads, and maintain precise control over alignment. The rope track method described here was not unique to one cabin or one homesteader. Variations of it appeared wherever heavy structures needed to move over difficult terrain. Logging camps moved bunkhouses and cook shacks on skid roads. Mining operations moved tipples and head frames on greased timbers. Railroad construction crews moved tool sheds and water tanks on temporary tracks. The specifics varied, different loads, different distances, different rigging, but the core logic remained. The broader principle is about treating buildings as systems. A log cabin is not a pile of logs. It is an integrated system, logs locked by notching, sealed by chinking, stabilized by roof framing, anchored by hearth mass. When that system is treated as a single rigid body and moved as a unit, the integration is preserved. When it is treated as disassembled components and rebuilt, integration is lost and must be recreated from scratch. The rope track method also demonstrates the value of borrowing techniques across contexts. The homesteader who moved his cabin was not inventing entirely new methods. He was adapting house-moving practice from cities, skid road practice from logging, and deadman anchor practice from construction and rigging work. Each technique had been developed for a specific purpose, but all shared common elements: controlled movement of heavy loads, reduction of friction, management of forces. Applying those techniques to a new problem, moving a log cabin away from an eroding bank, required understanding the underlying principles, not just copying procedures. The lesson extends beyond log cabins. In a landscape where rivers shift, where railroads push through mountains, where settlements rise and fall based on resources and access, the structures that survive are not always the ones that stay in place. Sometimes survival requires movement. The cabins that lasted longest were not the ones that stood their ground through sheer structural strength. They were the ones whose occupants understood that ground itself was not always stable and that structures could be moved when necessary. The rope track reconstruction encapsulates a wider truth about frontier engineering. Success often came from disciplined application of known principles rather than from heroic innovation. Reduce friction, spread loads, move slowly, maintain control. These are not complex ideas, but applied consistently with attention to detail and respect for the materials, they allowed one person to move a 5-ton building 60 feet uphill without breaking a single log. On that creek, and many like it, the cabins that lasted longest were not the ones that stood their ground, but the ones that learned how to move. If you value fact-grounded, technical frontier history, where numbers, tools, and real terrain decide the outcome, consider subscribing or supporting the channel so more of these detailed reconstructions can be researched and filmed.